Hey everybody, welcome to the review for exam 2. We're going to go over tons and tons of practice questions so that you can feel comfortable taking the exam. Let's dive in. Typically speaking, a researcher is interested in which of the following? That's going to be rejecting the null hypothesis. So letter C. Typically in research we set up a null and an alternative hypothesis. The alternative hypothesis is what the researcher kind of thinks is actually going to happen, but we have to be able to disprove or reject the null hypothesis in order to claim that the alternative hypothesis is in fact correct. Okay, the next question is, what is a p-value? The p-value is the probability of obtaining a score as extreme or more extreme as the one you observed if the null hypothesis was true. It's not the same thing as alpha, although we set alpha to a probability level of 0.05. What we're interested in finding is whether the p-value that we obtain, the p-value is going to be associated with either the slope of a regression line, or it'll be associated with the correlation coefficient, or it will be associated with finding a particular t value or a particular z value. The probability, the p-value, is, well, how likely is it that I would see the score that we found, whether that's a t-value or a z-score or whatever, if the null were actually true? And so if it's a very, very low probability, that means if the p-value is very small, and how small would you say? Well, smaller than 0.05, smaller than alpha. If the p-value is less than alpha, then you can say with pretty good accuracy that it's really unlikely that we would ever see such an extreme score here if the null were true. That's why we get to reject the null. And we say, oh, there's a very, very small chance that we would ever see this mean so high, or this correlation so high, or this slope so large, if the null was true. So therefore we get to reject the null hypothesis and conclude that the alternative is probably true, and there really is something going on here, whether it's a relationship or a difference between means from the population mean or something like that. So in this distribution, what we're looking at is a distribution of the age that babies begin to walk normally. And this was an example that I gave in class a long time ago. But the idea here is that we're interested in comparing a single baby and the age that they start walking after they take some kind of special vitamin that's supposed to increase the rate of their development. So maybe they start walking earlier than a distribution of babies who did not take that special vitamin. Okay, so what we do is we always have an alpha of 0.05. That's actually a probability of 0.05. That's kind of a p-value of 0.05. And that value of 0.05 helps us define 5% of the null distribution, the distribution that represents babies that have never taken this vitamin. And it helps us kind of cordon off this, what's called a critical region, okay? And the critical region could be on the left side of the graph or the right side of the graph, or if you have a two-tailed test, it could be split into both tails. It depends on what your alternative hypothesis is. So in this case, if the alternative hypothesis is this vitamin helps this baby walk earlier, then I'm interested in lower scores, right? Meaning less age. And so we cordon off this 5% under the curve because we always choose an alpha of 0.05, which is 5% of the curve. And then we find out, well, what z-score, or if you're thinking about a mean, what mean, which can be translated into a z-score, but it's a little different because that's using the sampling distribution of sample means. or what t-score is like the critical cutoff value that defines this critical region. If you look up in a unit normal table or the normal distribution table, what a p-value of 0.05, what z-score does that correspond to? It's going to be 1.64, and in this case, negative 1.64. So that kind of sets up a critical region where if we take a look at one single child and they actually start walking before that value, so they actually have a more negative z-score, maybe negative 2.3 or whatever, then they lie in the critical region, and that is going to be an extremely small p-value. Okay, the p-value associated with like whatever it is, negative 2.3 standard deviations below the mean, is going to be a lot smaller than 0.05. It's going to be smaller than 0.05 because it'll represent less of the distribution. So let's say we actually find out that this child that's been given this special vitamin, they start walking at 8 months, and that corresponds to a z-score of negative 2.00. So 2 standard deviations below the mean. Okay, well, what's the probability that we would actually see a child walk at 8 months or less given this null distribution? Well, if you look it up, the p-value for that is actually 0.0228. So 0.02 essentially. Well, that's less than our cutoff, the 0.05. That's less than alpha. And so there's a very, very small chance that we would ever see such an extreme score, such an extreme z-score. And by extreme, it could be a very extreme negative z-score in this example, or if you were interested in some kind of positive event, then it would be a very extreme positive z-score, right? Just for this example, we're interested in the lower part of the curve. So hopefully that makes sense. It would be very unlikely to see this child walk this early if the vitamin didn't do anything. And that would be the null hypothesis. So if the vitamin really didn't help this kid walk earlier, it would be extremely unlikely to find them walking at such an early age. And therefore, it's probably the case that the vitamin really does something to speed up development and help them start walking earlier. So we feel pretty comfortable rejecting the null hypothesis because the p-value is less than 0.05 and the z-value we calculated lies within that critical region, which automatically means the p-value is going to be less than 0.05 because it's less than 5% of the distribution. Okay, hopefully that made some sense. Let me know if you have any questions. By the way, what if we found out that that child who took the vitamin actually started walking at 11 months, which corresponds to a z-score of -1? Well, that's outside of the critical region. And if you look that up in the normal distribution table, you find a p-value, a probability of 0.1587, which is a lot more than the cutoff of p equals 0.05. That's the alpha level that we set, right? So there's actually a 15.87% chance that you would see a child walk at 11 months if the null hypothesis was true. So it's actually pretty likely that you would see a child start walking at 11 months if in fact the vitamin didn't do anything. So therefore we cannot reject the null hypothesis because it's actually pretty likely that in this case you would see a kid start walking at that age if the null was true, if the vitamin didn't do anything. So we didn't make it into our critical region, and the p-value is higher than 0.05, which is our cutoff, so we fail to reject the null hypothesis. Okay, I want to know if people with glasses tend to have a higher GPA than people without glasses. To test this, I would use, well, it's actually none of these. So correlations represent or measure natural associations between two variables. However, you have to have two numeric variables in order to do a correlation. Same thing with regression. You have to have two, or in the case of multiple regression, more numeric variables. So having glasses or not having glasses is a categorical variable, and therefore that would actually be what's called an independent samples t-test, which we'll get to later on. All right, I want to know, what does the value of negative 0.53 mean in this table? Well, if you look at the negative 0.53, that corresponds to a Pearson's R, which is a correlation between stress and sleep. So that means that people who have higher stress tend to have lower sleep, or alternatively, people who have higher sleep tend to have lower stress. So as one of the variables increases, the other variable is going to be decreasing. That's why it's a negative correlation. Now, is that correlation significant? The answer is yes, and you can tell that because the p-value, which is just underneath that Pearson's R, is 0.021. Well, we compare that to the alpha level, which is always a p-value of 0.05 in this class, and if it's less than that, you know that the Pearson's R is basically more extreme than some cutoff value. Okay, and so therefore it would lie in a critical region. And again, we could translate the Pearson's R to a t-score and actually find a t-critical value, and then see if the t-score that corresponds to this R value is actually more extreme than that, the critical t-value, and lies in the critical region, and therefore we get to reject the null. We can do all that stuff, but this table just tells you straight up, this is the p-value, 0.021. And if that's less than 0.05, it is significant. That means that sleep and stress are significantly related to one another. Okay, let's say that I have an alternative hypothesis that the more credit hours someone takes, the less sleep they get. Based on the information in this table, what should I do? Well, I'm going to have to, unfortunately, fail to reject the null hypothesis. The null hypothesis would be that credit hours and sleep are not related at all. I can't reject that because you can see that the p-value associated with credit hours and sleep for the Pearson's R, the p-value is 0.072. That's above our cutoff, our alpha, of 0.05. And therefore, we fail to reject the null hypothesis. All right, we've got some multiple regression output here, and it looks a little scary, but it's really not that bad when you take it bit by bit. So the first thing I want to know is, well, we're looking at stress as the outcome variable, the dependent variable, and we're looking at credit hours and hours of homework as the independent variables, the predictor variables. Okay, so this is a multiple regression because we've got two predictors and one outcome variable. What I want to know is which value out of all of these numbers, which value represents the combined effect or relationship between credit hours and hours of homework on stress. That number is represented by capital R, and it is 0.862. And remember, capital R is basically the multiple correlation coefficient. So it's like little r, which is Pearson's R, just a bivariate correlation, but it's capital R. It can handle more than relationships just between two potential variables, but it is a correlation. Okay, moving on. I want to know, is the entire model, model 1, which is the entire model being credit hours and hours of homework predicting stress, is the entire model significant or not? Yes, it is. How do I know that? Okay, so you go to the second kind of table, which is titled ANOVA, and you look at the F statistic and the p-value associated with it all the way at the right-hand side. And you can see that the p-value is less than 0.001. Well, anything less than 0.001 is definitely less than our cutoff value for this class, which is 0.05. And so, yes, the entire model as a whole is a significant model. All right, next question. Please interpret for me the slope of hours of homework. So first of all, where is the slope for hours of homework? When you see the unstandardized column, that is B. That is the slope for these two different variables, credit hours and hours of homework. So you can see that the slope for hours of homework is 0.813. What that means is for all slopes, excuse me, the interpretation is for every 1 unit increase in the x variable, the predictor variable, what happens to the y variable? So what we're looking at with 0.813, this says for every 1 hour of additional homework you have, your stress will increase, we predict, by 0.813 units of stress, whatever, scale that was on. So that is how you interpret that. For credit hours, you would look at this and say for each 1 additional credit hour that you take, your stress will increase by 0.019 stress units. All right, next question. Does the amount of credit hours that somebody takes significantly predict their stress controlling for hours of homework? The answer is no. So if you go to the credit hours row, you can see that it has a slope of 0.019, okay? The t-value associated with that, which we're not worried about too much, 0.090. And the p-value associated with that is 0.930. That is a lot larger than 0.05, which means credit hours is not a significant predictor of stress when you're controlling for hours of homework. So when hours of homework is in the model, basically it's going to be a much more powerful predictor of stress than credit hours. And you can see that also by looking at the standardized beta. They're called beta weights or beta regression coefficients. If you look at this standardized beta column, you can see that for credit hours, it's 0.019, and for hours of homework, it's 0.850. The larger number here, and I mean larger as in more extreme, because if it was a very large negative number, that still counts. But since both of these are positive, you just see which one is the larger number for the standardized betas, and that means it's a better predictor. It's a more powerful predictor. It has a larger effect on the outcome. So hours of homework here you can see is a significant predictor at p of 0.002, controlling for credit hours. But credit hours is not a significant predictor of stress when controlling for hours of homework. By the way, the intercept, you can see, is negative 4.603, and the p-value is above 0.05. So but what does that mean? We don't really care about that. The intercept is just sort of the intercept. Whether or not it's significant from a p-value standpoint is sort of irrelevant, because don't worry about that at all. The intercept is just always going to be the intercept, and it doesn't matter if it's significant or not. But what you do care about is whether the predictor variables are significant predictors of the outcome. Okay, and finally, what does an adjusted R-squared value of 0.697 tell you? that value, 0.697, tells you the proportion of stress, or the proportion of variability in stress, that is explained by both credit hours and hours of homework. And so in kind of plain English, we would say 69.7% of the variability in stress can be explained by credit hours taken and hours of homework. So that's quite a bit of stress is explained by hours of homework and credit hours, right? Which makes sense. The more credit hours you have and the more hours of homework you have, the more stressed you're probably going to be. Okay, let's say I want to know whether a correlation is significant or not. What is the critical value for t if n equals 22? And we're going to assume a two-tailed test. So you need to remember that when we're talking about correlations, the degrees of freedom associated with correlation is n minus 2. So 22 minus 2 is 20. So we're looking at this table of t critical values. We have a degrees of freedom of 20. We know it's going to be a two-tailed test because I told you that in the prompt. And we always use a cutoff value, an alpha level of 0.05. So we just use the row for degrees of freedom of 20, the column for the two-tailed test with 0.05 as our alpha, and we get a critical t value of 2.086, and we're going to round that to 2.09. What that means is if our correlation coefficient, once we translate that R value into a t value, if the t value is more extreme than this 2.09 critical value, if our calculated observed t value is more than that, if you were interested in something being larger, if you were interested in something being smaller than something else as your alternative hypothesis, then it would be negative 2.09. If it's more extreme than 2.09, then you can say that it's in the rejection region or the critical region. You get to reject the null hypothesis, and you know that the probability of observing such a large or such a small, let's just say a more extreme t value as the one that you observed would be less than 0.05. The probability would be less than 0.05 because we're in a more extreme region of the distribution. Okay, everybody, we're going to do a lot of questions based on this raw data right here. So please pause the video, take a screenshot of this, and put it somewhere that you can continuously refer back to. What we can see here is that we have 5 participants, okay, and they've given us data on several variables. So whether or not they own a smartwatch is just no or yes, that's a categorical variable. The number of phones they own, the number of laptops they own, and the number of times they check their Instagram, let's say, in an hour. Okay. What I've done here is given you the deviation scores and the means and the variances for each of the numeric variables, as well as the deviation products for phones and Instagram checks. But you'll see several question marks for the actual raw scores. How many phones does each participant own? How many laptops? How many times do they check Instagram? Those you don't know. And so you're probably going to have to figure something out. But we'll do a bunch of questions related to this data. So again, make sure you save this somewhere so that you can refer back to it. First question. I have a hypothesis that the more phones people own, the more they check Instagram. If I conclude that having more phones does lead to people checking Instagram more, when in reality it does not, I would be making a type 1 error. If I think something is actually happening, but the reality is that it's not happening, then I've made a type 1 error. That means if you think that you can reject, or if you've rejected the null hypothesis, but in fact the null hypothesis is true, which you can never know, but if in reality the null hypothesis was true and owning more phones doesn't have anything to do with checking Instagram more frequently, then you've made a type 1 error because you thought that, yes, these two things are related when in fact they are not. Imagine a participant has 10 phones. Calculate the z-score for this participant. So in order to solve this one, you have to get the raw score, which is 10, of course. You subtract the mean from our sample, the mean number of phones people have, which was 4. And then you have to divide that by the standard deviation. Well, I didn't give you the standard deviation, but I did give you the variance. How do you transform variance into standard deviation? You just take the square root of it. So I gave you the variance, which was 10. If you take the square root of 10, it's about 3.16. So 10 minus 4 divided by 3.16, with rounding, will get you to 1.90. All right, based on that statistic you calculated in the last question, and assuming a one-tailed hypothesis that this person owns more phones than our sample, what would you conclude? Assume an alpha equals 0.05. Okay, so you take that z-score that you calculated for a single person, and their amount of phones is 1.90 standard deviations above the mean of the sample. So you find a z-score of 1.90 on your normal distribution table, and we're interested in the smaller portion, and specifically the positive smaller portion, because this is a z-score of 1.90, so it's above the mean, and we think in our alternative hypothesis that this person does in fact have more cell phones than the average. So we look at the smaller portion because we're interested in basically the top 5% of the distribution, since alpha is 0.05. And we find a probability of observing a z-score at 1.90 or higher. The probability associated with that is 0.0287. Now, is that value more than or less than our alpha value? Is it more than or less than a p of 0.05? Well, it's less than 0.05. So in this case, we would reject the null. We would actually have a z-score that's in the rejection region, and it's actually a very low probability that we would see such a high z-score, meaning there's a very low probability, 2.87% chance, of seeing somebody with 10 cell phones if the null was true. The null in this case, meaning that there's no difference between the amount of cell phones they own and the amount of cell phones that the average person in our sample owns. So there's a very low chance that we would ever see someone owning 10 cell phones if in fact that number was not different at all from everyone else who had cell phones in our sample. Therefore, we reject the null hypothesis. Okay, still based on the statistic you calculated in the last question, meaning the z-score. Now we're assuming a two-tailed hypothesis. What would you conclude about the null and alternative hypotheses? Now this is a little tricky because there aren't any two-tailed tests that are associated with your normal distribution table. But what you have to remember here is that when alpha is 0.05 and you have a two-tailed test, you actually have to split alpha in half. So 0.025 on the lower end of the distribution and 0.025 on the upper end of the distribution. Okay, so that corresponds with 2.5% of the distribution on the higher tail and 2.5% of the distribution on the lower tail. And so in that case, when you're looking at this normal distribution table, you'd actually want to see if the p-value associated with the z-score of 1.90, if it's above or below the value of 0.025, okay, so that is the difference between a one-tailed and a two-tailed test here. And what you can see is the p-value of 0.0287 is not less than 0.025. It's more than 0.025, which means that for a two-tailed test, a z-score of 1.90 is not extreme enough. It's not extreme enough to end up in the rejection region. And the probability of finding a z-score of 1.90 is greater than alpha in this case. Well, it's greater than half of alpha. And so you actually fail to reject the null hypothesis that 10 cell phones is more than the average cell phones. All right, getting back to our data here. I'm interested in the correlation between the number of phones somebody owns and the number of laptops they own. The first thing that I need to do, and the first thing that I'd like you to do, is calculate the covariance of phones and laptops. All right, so on an exam, you would actually be given this Excel data file, and so you could open it and work in Excel. Remember that the covariance is the sum of the products of the deviations from X and the deviations from Y for each participant divided by n minus 1. So in order to figure that out, you'd have to get the deviations for phones and the deviations for laptops, and fortunately that's already here. It's already in the data. But you have to create a new column that would be the deviation products. The deviation products. So you'd have to multiply all of the deviations of phones times the deviations of laptops for each participant. And that would give you this column over here. I usually name it something like dev products or dev prod or something like that. It's just the products of the deviations. So you can see that that resulted in deviation products of 4, 0, 4, 2, and 8. And then you have to add all those deviation products together. So that's the little sum column over there, or row rather. The sum was 18. But that's just the numerator. That's the sum of the deviation products. You have to divide that by n minus 1. So you would take 18 and divide it by 4, because there's 5 people total. 5 minus 1 is 4. 18 divided by 4 gives you a covariance of 4.5. And you will probably be expected to do stuff like this on the exam. So it's a really good idea to get practice to actually make sure that you can do this on your own. Okay, now I'm interested in what is the correlation between phones and laptops, the number of phones somebody owns and the number of laptops they own. All right, well, we have to remember, how do we find the correlation coefficient in the first place? You have to divide the covariance by the products of standard deviation of X and standard deviation of Y. Well, again, the standard deviation wasn't originally on this Excel sheet. What you'd need to do is just take the square root of the variance for phones and the variance for laptops. That gives you the standard deviation. By the way, you can do that very easily in Excel. There's a command if you just type in equals and then I think it's SQRT. That'll give you the square root function, and then you just click on the variance cell, which would be 10 or 2.5, and then it'll spit out the standard deviation for you. Or you could just do it on the calculator and type it in manually, whatever you want to do. So then we have the covariance, then we have the standard deviations of phones, standard deviation of laptops. We just divide the covariance, 4.5, divided by the products of 3.16 and 1.58, and you end up with a correlation coefficient R of 0.90. Okay, based on the statistic you calculated in the last question, and assuming a two-tailed hypothesis that phones owned is related to laptops owned, what would you conclude about the null and alternative hypothesis? Well, in order to do this, you're going to have to transform your correlation coefficient R into a t-score and then compare it to a t-distribution based on our alpha of 0.05, two-tailed test, and the degrees of freedom of n minus 2. So let's first calculate the observed t-value that corresponds to our R value. So if you were to do the math, we just calculated a correlation coefficient of 0.9. So it would be 0.9 times the square root of n minus 2. There's 5 people in the sample, so 5 minus 2. Divide that by the square root of 1 minus R squared. So that's 0.9 squared. If you do the math, you would end up with an observed t-score of 3.58. Now what we have to do is compare our observed t-score to the critical t-score for the degrees of freedom, n minus 2, alpha 0.05, and a two-tailed test. If our observed t-value that we just calculated is more extreme than the critical t-value, then we know we're in the rejection region, the critical region. We can reject the null hypothesis. We have a significant relationship between these two things, a significant correlation, and we know that the probability of observing such a high t-value is less than 0.05, is a small probability of seeing that if the null hypothesis were true. So all of that stuff happens, all of that stuff is simultaneously true. So let's find out. Let's compare this observed t-value to the critical t-value. Okay, so we go back to the t table, and we need to look up a degrees of freedom of n minus 2. So that's 5 minus 2 is going to be 3. So we're looking in the row for 3 degrees of freedom. We have a two-tailed significance test, because I told you that in the prompt, and we always use an alpha of 0.05. So we go degrees of freedom of 3 is the row, the column is 0.05 for the two-tailed test. So our critical value of t is 3.182, and that critical value of t, 3.182, sets up the rejection region. So anything more extreme than 3.182 is the rejection region or the critical region. Remember that the t-value that we actually just calculated based on our R of 0.9 was 3.58, and that's more extreme than 3.182. So we know without a doubt that our observed t-value is in the critical region. We reject the null hypothesis, and we can conclude that in fact there is a significant relationship between the number of phones owned and the number of laptops owned, because this will also tell us the probability of observing such a high t-score of 3.58. If the null hypothesis were true, meaning the null hypothesis that laptops owned and phones owned are not related, is going to be less than 0.05. And you know that because we're already in the critical region. The t-value we observed is in the critical region. It's more extreme than 3.182, and 3.182 is based on an alpha of 0.05. So that's the probability of 0.05, 5% of the distribution, the t-distribution, and our value was more extreme than that, which means there's even less probability of that happening if the null was true, so we reject the null. All right, hopefully that makes some sense. All right, a little bit different variation now. Let's say I have a hypothesis where I think that the number of phones somebody owns can predict the number of laptops they own. And so what I want you to do is calculate the slope for the predictor variable. Calculate the slope for the predictor variable from what I just said. All right, how do I calculate the slope for a predictor variable? Well, b, which is the slope, equals the covariance of x and y divided by the variance of x. Well, lucky us, we already have all of those numbers, right? We already calculated the covariance, which we found to be 4.5. And we have the variance. I gave it to you at the beginning. The variance for number of phones, which is the predictor variable, is 10. So all you have to do is divide 4.5, the covariance, divided by 10, and you get a slope of 0.45. How would you interpret that slope? The interpretation of the slope is for every additional phone somebody owns, we would predict that the number of laptops they own increases by 0.45. All right, so we've got the slope for the number of phones and how that's related to the number of laptops. But now, remember in regression, we're all about trying to figure out the equation for the line of best fit. So now we need to figure out the y-intercept. So please calculate the y-intercept for a line of best fit that is trying to predict the number of laptops owned from the number of phones owned. Well, to find out the y-intercept, which is denoted as the letter A, you need to take the mean of the y variable and subtract the product of the slope and the mean for x. Well, we've got all those numbers already, which is great. So you take the mean of y, which is 2, that's the mean number of laptops people own, 2, subtract the slope, 0.45, times the mean of x, and people owned an average of 4 phones. So you take 2 minus the product of 0.45 and 4, and you end up with a y-intercept of 0.2. And what does that mean? What is the y-intercept? The y-intercept is the value of y when x is 0. So if somebody has 0 phones, we would expect them to have 0.2 laptops. All right, let's say May owns 11 phones. How many laptops would we expect her to own? To find that out, we need to construct the equation for the line of best fit. And we already know those things. We just calculated them. So the predicted value of y hat, equals the slope times the x value, the 11 phones, plus the y-intercept. So 0.45 times 11 plus 0.2 gives us an expected value of y of 5.15. So if May has 11 cell phones, we would expect that she also owns 5.15 laptops. What is the critical value of z for a two-tailed test if alpha equals 0.05? So to find the answer for this question, you have to go to your z table, your normal distribution table, and you're actually looking for the p-value of 0.025 because this is a two-tailed test. And so we have to split alpha in 2. So 0.05 divided by 2 is 0.025. And so we're looking for the z-score that corresponds with the value of the p-value or the alpha level of 0.025. So all you do is you actually have to look up, like go hunting for the p-value of 0.025, and then go to the left to find what's the corresponding z-score, and it is 1.96. Now that is, in a two-tailed test, that means both we're talking about positive 1.96 on the upper end of the distribution, and anything below negative 1.96 on the left side or lower side of the distribution because it's a two-tailed test. As a visual representation of this, when you have a z-score distribution that is perfectly normally distributed, like the standard normal distribution, when you have a two-tailed test where you have to split alpha into 2, therefore it's only talking about 2.5% of the distribution on the left, 2.5% of the distribution on the right, or a 0.025 p-value. You look at the z's, the z-score is down below. Again, that corresponds to negative 1.96 and positive 1.96 if it's a two-tailed test. If you're only talking about a one-tailed test, so alpha is 0.05 and you don't have to split that. If your hypothesis is having you interested in the upper end of the distribution, like you think something is more than something else, then that corresponds to a z-score of 1.64. If it was a one-tailed test, but you were interested in something being lower than something else, like drug A reduces depression scores compared to people who don't take drug A, then you'd be looking at the bottom 5% of the distribution, which would be a z-score of negative 1.64. So those are good values to just kind of have in your back pocket or to kind of memorize. The value of a statistic that has the same corresponding p-value as your alpha level is called what? That is going to be D, the critical value. When you try to look up in a table for an alpha level of 0.05, what's the critical value? Let's say you're using a t-table. That means it is the t-score that corresponds with exactly 5% of the distribution, whether that's the upper 5% or the lower 5% if you're talking about a one-tailed test, or the upper and lower 2.5% if you're talking about a two-tailed test. So the z-value or t-value that actually corresponds with your alpha level of 0.05, that is the critical value, and it sets up the critical region. And then if you're actually observed statistic, when you calculate the z-score or the t-score for the correlation, or you have to do a z-score transformation of a mean or something, if it's more extreme than the critical value, then you're in the critical region. You can reject the null hypothesis. Your p-value will be less than 0.05. It's going to be less likely than 5% chance to see such an extreme value if in fact the null hypothesis was true. Therefore you get to reject the null hypothesis and conclude that your alternative hypothesis is correct. If the null hypothesis is true, what would be the most likely value of R? All right, so what is this question asking? It's saying, if you're talking about a correlation between two variables, if the null hypothesis was true, what would the relationship kind of look like? The strength of the relationship look like between the two variables? Well, we're talking about the null hypothesis. The null hypothesis for correlations is that there is no relationship between the two variables. If there's no relationship, then R should equal 0. Okay, or very close to 0. If R is 1.0, that is a perfect positive relationship. If it's negative 1.0, that's a perfect negative relationship. And that's incredibly strong. I mean, that's the strongest possible relationship that you can have for a positive or a negative relationship. And almost certainly that would have to reject the null and conclude that in fact there is a significant relationship between the two variables. So the answer for this is C, 0. All right, study hard and best of luck on exam 2.